Hi everyone, welcome back. Welcome to a new series that I wanted to do on antennas and arrays. I wanted to do this series because I feel like there are some topics that are not covered by other videos on YouTube in the area of antennas and arrays. And so I thought I'll make some videos explaining how I do things. Hopefully it's helpful. So in the first video, I wanted to show you how you can design and optimize uh, different antennas or different structures in HFSS using optimization controlled by MATLAB. So HFSS has an inbuilt optimization, which I don't usually use. I usually use MATLAB. So I just wanted to show you how you can do that. So as an example, we'll start with designing a U-slot patch antenna. So I'll divide this into two videos. So in the first video, we'll cover how to basically draw the layout of a U-slot patch antenna for a PCB. And we'll run a simulation, plot some results, and then I'll show you how you can optimize the design using a very efficient optimization tool from MATLAB. So let's get started. We open HFSS. This is what you should see. So maybe I'll say, okay, once you open HFSS, let's first save this. So let me say I will save it to this tutorial. So I'll call it U-slot patch antenna. Okay. Then we want to insert HFSS design. And I'll call this the U-slot patch. Okay. Next thing is we go to HFSS solution type and make it driven model. That's good. And now we want to draw our antenna. So let me get started on that. So let's draw the substrate first. So I'll click on a box, make a box. Let's call this substrate. And then I'll call this minus. So I'm just giving it some dimensions. Substrate width, substrate length divided by 2, and minus substrate height divided by 2. So let's say the substrate width is 25 millimeters, length is also 25 millimeters. And the height of the substrate, I'm going to set it based on the thickness of two dielectric layers. So I'll say the first one is 1.524 millimeters, and the second dielectric is 0.813 millimeters. Maybe I'll explain where those numbers came from. Okay, so Control D will zoom out. So this is the substrate. I'm going to make it transparent. Okay, so how did I pick the size of my substrate? So you can go to like any PCB company, so let's say PCB Way, and then you can say, okay, you want to use Rogers 4003 substrate. What options do they have? They have these options, right? So I picked this and this. So it's two-layer PCB. You need actually a thick substrate for a U-slot patch. So I picked these two with no metal between them. And that's how I got that thickness. You can choose different values. Okay, so that's the substrate. So I hit F to select face. I select the top face, click Control B to go to the bottom face. Then right click, edit surface, create object from face. So that creates a metal sheet on the bottom surface. And then right click, edit surface, thicken sheet. And I'll thicken it to the thickness of copper, which I'll set as a variable. It's copper thickness. And this is about 35 to 50 microns. So I'll just set it to 50 microns. Okay, and then let's make this copper colored, I guess. Okay, so now that's what that looks like. So the reason I did it this way rather than making a new layer is that now it will just scale with the original substrate because it's tied to this box. Okay, so we have the ground plane. I'll call this the ground plane. Ground, let's say. And now we want to draw our patch, right? So let's make another box, call this patch, and let's change its dimensions. So minus of patch width divided by 2 minus patch length divided by 2, comma, and the location is Z location is substrate height divided by 2. So let's say patch width is around 10 millimeters and patch length is, let's say, 6.5 millimeters. Patch width, patch length, and this is copper thickness. Okay, so there we have our patch on top of the substrate. I also want to make this the same color. There we go. And we'll also make this a little bit transparent. Okay, so now we have a patch, we have the ground plane. So now we need to make a feed. So I'm going to make it probe fed from the bottom. So I'll make a cylinder. So I'll call this feed dielectric. Okay. So how do we set this? So we'll say, okay, feed location is feed X and feed Y. And the Z location should be, let's say, minus substrate height divided by 2. So let's just say this is 0 millimeters, 0 millimeters. And the radius should be dependent on the connector, the SMA connector that you use. So the one that I've used in the past is around 0.15 millimeters. And the height is, let's say, minus of feed length, which we'll set to 1 millimeter. Okay. So you see that's the feed there. Actually, I made a mistake. The feed radius I'll call this feed radius, feed dielectric radius. And this should be 0.5 millimeters. Okay, yeah, that looks right. So I'll make this white color because it's going to be Teflon. Now that's what that looks like. I also want to make the ground transparent so we can see what's underneath. Okay. All right, so the next thing we need to do is make a conductor around this substrate, around the feed dielectric. So I hit F to select faces again. Select this. So you select the faces. Again, right click, edit surface, create object from face, edit surface, thicken sheet, copper thickness. There we go. So now we have metal around that. Let's change the color to orange. And that should look like that. That's good. Now we also need to make the center conductor that comes and connects to the patch in the center, right? So for that, I will make a copy of the feed dielectric and call it feed center. And we'll call this feed wall. Okay. So feed center, I'll just make it orange. And then we can only need to change the feed center radius, which I'll say is around 0.15 millimeters. Okay. There's one more thing I need to change because it needs to come and touch the patch now. So this would in fact be plus substrate height divided by 2 plus the copper thickness. So it comes all the way to the patch. And you want to make the height minus substrate height minus copper thickness. Right, so now it comes all the way from up here. So let's look at this. It starts from this copper thickness and this whole substrate thickness, and then comes all the way down to this end, right? Okay, so now we can play around with this a little bit just to see how it works. So if I make this 5, then it goes to the right. If I make it 5, it goes up. So let's bring it back to the center. You can move the feed around. Now, one thing you need to do is you need to subtract the ground plane, and make a hole here basically, so that the feed can actually come through, right? So what I'll do is I'll subtract the feed dielectric from the ground plane. And I also want to make a copy because you don't want to lose the feed dielectric. That's it. So now the ground plane has a hole, right? Okay, so almost ready with the patch. The last thing we need to do is we need to make a port cap because I want to use a wave port here. Maybe I'll cover wave ports and lump ports in a separate video, but we need to use a wave port here because it's an SMA, right? So I'll say again, hit face and F and then click on this face. Right click, edit surface, create object, edit surface, thicken sheet to copper thick. Doesn't matter the thickness so much. And then I'll click on the edge here, edit surface, move faces along normal, and again the copper thickness. So that gives us sort of this cap on top of the edge of the feed, the end of the feed. And I'll change this one's color to maybe blue because it's not a metal. It's not part of the design basically. It's just required for the simulation. Okay, nice. Let's assign some materials now. So we have feed center. This is, I'll call this the port cap. Okay, so we have feed center, feed wall, ground plane, and patch, right? All of these are copper. So I'll right click assign material and we want to assign copper. So I guess it has to load the materials. Okay, there we go. So copper, that's it. Okay, then feed dielectric. This should be Teflon. Okay, port cap should be PEC. And substrate should be Rogers 4003. So this one. Okay. In reality, actually, if you use two, yeah, we actually have two dielectric layers back to back here, right? You need to add a pre-preg layer between them. But I don't want to go into such technical details now. But if you're actually fabricating this, just make sure that you have a pre-preg layer that's included in the simulation. Pre-preg is kind of this bonding layer between two dielectrics. But anyways, in this case, I have ignored that, but it shouldn't change things too much. Anyways, okay. The last thing we need to do is we need to cut a slot inside this, right? Okay, so let's do that. So to create the slot, I'll make a copy of the patch and I'll call this the slot or the U slot, I guess. Let's call this U slot. Okay, so I'll say minus slot width and slot thickness. So I'm going to make the slot width 2.65 millimeters and the slot thickness as 1 millimeter. This should be slot width, slot thickness. That's it. Okay, so we have a rectangular slot. So how do you make it into a U slot? Click F, select these two faces, right click, edit surface, create object from face, then again edit surface, thicken sheet, slot thickness, and once again edit surface, click the face, these two faces, edit surface, move faces along normal, and I'm going to call this the slot length or slot L. Make this 3.5 millimeters. So there we go. That's our slot. One more thing I need to do is I need to give a slot, this slot a Y position. Plus slot Y. I'll call this 2 millimeters. Okay. Okay. One thing I do want to change is that we can just set this to be just slot Y. It doesn't matter. It's just the way I had it before. So I just want to have it consistent in that sense. Okay. All right. So let's bring this slot down. So to do that, we need to set the slot Y position to minus 1.33. Actually, to make it consistent with what I had before, I'll redo this a little bit differently. So what I had before was my previous results that I ran this with. Right click surface, create object from face, edit surface, thicken sheet, slot thickness, and I had the slots actually, the arms of the slot going on this side earlier. Surface, move faces along normal. Slot. Okay, that's better. And the slot Y position should be 1 point. Okay, that's right. Okay, so now we have the slot. We can select these three objects and then unite them. And then subtract that from the patch. Okay, that's it. So there you have your use slot patch, right? Okay, so one thing I'd like to do at this point is that I want to reorganize these variables so that I have my variables of interest in the front, right? So I'm going to move slot width up. Then we have slot length. These are the variables I care about the most, right? Slot Y, then slot thickness, maybe then patch width, patch length, and the feed Y. Okay, so these are sort of the most important variables that we will be sweeping over, right, to optimize this design. So let's recap. The slot width should be, let's say, 2.65. Slot length is 3.5. Slot Y is 1.33. Thickness is 1. Patch width is 10. Patch length is 6.5 around. Feed Y is 0, let's say. Substrate width is 25. So we don't really need to change these. So I haven't reordered these. We only change these 7 variables up to feed Y. Okay, so I think we're pretty much done with the 3D model. So one thing I would like to do now is to say right click that, design settings, and enable material override. We need this because we have many dielectrics that are overlapping. Okay, and we'll create a boundary open region. Right click, create open region. We are gonna make it at 10 gigahertz. So let's say 10 gigahertz radiation boundary. There you have your boundary box, radiation box. Next thing you need is excitations. So I'll go here and then I'll click face. So I click F, click this face, click back, a control B to select the face of the where I want to assign the port. Then edit right. You know what? I could do this. I could select the port cap, view only the port cap, select the top surface, right click, assign excitation, port, wave port. And since it's a coax, there's no need for assigning polarity. Not renormalize, finish. Okay. So we've assigned an excitation, we've assigned boundary, need to assign an analysis. So we'll simulate at 10 gigahertz, 20 passes, and at least 2 converged passes. Hit OK. And then let's simulate this from 8 to 12 gigahertz, so the X band. Put on points, and we can save the radiated fields. Okay, that should be pretty much it for this design. Let's check, validate. It's all good. Okay, save it, and then let's run it. So once it's done, I'll resume. Okay, so that took just a couple of minutes, and the simulation is done, as you can see. So when you hit O and then select an object, selects the entire object. So another, I guess, thing to know about HFSS is if you make a box from the left side, it selects everything inside the box. And if you make it from the right side, it selects everything that the box is touching. These are just some tricks, I guess. Anyway, so let's take a look at the results. Let's look at S11. Okay, it's obviously not very good. It's not really matched, but we will match it. Can also look at gain, I guess, but it doesn't make sense. Okay. So what I'll do now is I have some variables that I've already found what the value should be. So let me set those 2.65088. It should be 3.7059, 1.33417. Slot thing is 0.992386. Patch width is 10.3568. Patch length of 6.81084. Feedwise minus 1.18848. So how did I get these exact values? We'll cover in the next video. But with these values, let's run the simulation again and see what we get. Okay, let's just run it. Validate, analyze. Once it's done, I'll continue. Sorry, one mistake I noticed is that for some reason there's an extra copy of the patch that wasn't deleted. So now that it's deleted, now we have just the use slot patch. Okay, so with these results, I am going to simulate this use slot patch now with these values, and then let's see what that comes out to be. Because the results were not right, so I was just wondering why that happened. Okay, so now I resimulated it, and then let's see what happens. Okay, so the simulation is almost done. There we go. Okay, so this looks really nice, right? It's below -10, and then I can place a marker, and then we see that the bandwidth is 20% or so. So that's very nice. We can also look at some other results. So let's make a far field setup. I'll call this my sphere. Oops. Okay. 0, 90, 90. Go from minus 180 to 180 with 1 degree steps. Okay. So now we can create some far field results. Create far field result. Sweep. Choose my sphere. I want to look at the realized gain. I'm not going to go over what this means, but if you pick up any antenna book, you should be able to figure it out. Okay. 10 gigahertz. Let's look at what the gain is. Sort of the gain pattern, I guess. It looks nice, sort of like a patch. And then, of course, you can look at it at different frequencies. So we can look at close to 8.5. It also looks nice. We can look at the 3D pattern. So again, let's look at the realized gain 3D pattern. So that looks like a nice radiation going up both sides, right? One more thing that's sort of interesting to look at would be the realized gain over frequency along bore side. So we set this to be 0 degrees. Say 0 degrees. And Okay, phi 0, theta 0. Guess it didn't matter that I changed that, but anyways. Okay, let's look at that. Oops, this should be over the sweep. Apply. And that looks very nice, right? Very broadband pattern. One more thing you can look at is the radiation efficiency, antenna parameters. You can also look at peak realized gain over the entire frequency. So the previous one was bore side gain. Now we're looking at the peak gain, right? Also very similar, which means that most of the radiation is going along bore side, right? So we can say, okay, copy data, put it here, paste. So they're very close, which means that for the most part, the radiation is going along bore side, right? Okay, then we can also look at the efficiency, radiation efficiency and total efficiency. They're both slightly different. I'll let you figure that out, but we'll look at both of them. And of course, total efficiency depends on the matching, whereas radiation efficiency only depends on the loss. So it's very nice. It's more than 85%. So it's a very nice antenna, and that's why it's a very popular antenna for wideband performance. For about 20% is what you can get from this kind of an antenna. So, okay, one thing, so the elephant in the room is how did I actually end up with these numbers? Because they seem kind of arbitrary. And that's where the optimization comes in. So in this video, I'll stop here. I'm going to make a follow-up right after this, explaining how I did that, how I got these numbers. Okay, so I'll see you there. Thank you.